Hi all, I am Shala Rose, Assistant Professor in Triple Department from Emmanuel's JJ College of Engineering. Now I am explaining about synchronous motor. Actually, the synchronous motor is widely used in the industrial applications. This motor runs at the constant speed and it does not depend upon the torque acting on it. So it has the constant speed torque characteristics. The efficiency of the synchronous motor is around 90% to 93%. The synchronous motor is a W-fed motor. The three-phase supply is given to the stator while the rotor is fed from the DC source for expression of the field winding. The three-phase supply is given to the stator of the three-phase alternator. It can act as a motor as it driven as a synchronous speed. It is called a synchronous generator. So if alternators is run as motor, it will rotate at a synchronous speed. Such a device is which converts the electrical energy into mechanical energy running at synchronous speed is called synchronous motor. Synchronous motor works on the synchronous speed and cannot work at the other speed than the synchronous speed. The speed is constant irrespective of load. Next one is rotating magnetic field. Rotating magnetic field can be defined as the field or flux having constant amplitude but whose axis is continuously rotating in a plane with a certain speed. Next, the construction of the synchronous motor. There is no constructional difference between synchronous motor and synchronous generator. Similarly, in the DC machine, where there is no constructional difference between the synchronous generator, motor and generator, by the same way, the synchronous motor and synchronous alternator have the same construction features. Uh, it has a two part, one is stator, another one is rotor. The stator is consisting of three-phase star or delta controller winding. This is excited by the AC supply, that is three-phase AC supply. The rotor is a field winding, the construction of which rotor is salient pole type or cylindrical type. Practically, most of the synchronous motor use the salient pole type. The field winding is excited by the DC supply through the slip ring. Uh, Next, the stator. First of all, we have to see about stator. The stator is a stationary armature. This consists of core and the slot to hold the armature winding, similar to the armature of the DC generator. The stator core uses a laminated construction. It's built up of the special steel scabbings instead of from each other with a varnish or paper. The laminated construction is basically to keep down the eddy current losses. Generally, the choice of the material is steel to keep down the hysteresis losses. The core is fabricated in a frame made of the steel plates. The core has a slat on its periphery for housing the armature conductors. Frame does not carry any fluxes and serves as a support to the core. Ventilation is maintained with the help of the holes cast in the frame. Next one is rotor. Uh, there are two types of rotor. One is salient pole type and next one is cylindrical type. The salient pole type is also called as the projector pole type, as all the poles are projected out from the surface of the motor. The poles are built up of the thick steel laminations. The poles are bolted on the rotor. The pole face has been given a specific shape. The field winding is provided on the pole shoe. These rotors have large diameters and shell axis lengths. The limiting factor of for the size of the rotor is centrifugal force acting on the rotating number of the machine. As mechanical strength of salient type is less, this is preferred for low speed alternators ranging from 125 rpm to 500 rpm. The prime movers are used to drive the such rotor and generally water turbines and IC engines. Next one is smooth cylindrical type. This is also called as the non-salient type or non-projectile pole type rotor. The rotor consists of smooth solid steel cylinders having number of slots on the accumulative field coil. The slots are converted to the top of covered at the top with the help of the steel or manganese wedges. The unstructured portions of the cylinder itself act as the poles. The poles are not projecting out and the surface of the rotor is smooth, which maintains the uniform angle between the stator and the rotor. These rotors have the small diameters, large axial lengths. This is to keep the peripheral speed within limit. The main advantage of this type of the is mechanically very strong and is preferred for the high speed alternators ranging 1500 to 300 rpm. Such motor is called the turbo motor. Next one is the working principle of the synchronous motor. Actually we give the three-phase supply to the stator winding and three-phase AC supply to the stator winding and uh, three-phase AC supply to the stator winding and the uh, rotor we have the DC supply. The synchronous motor works on the principle of the magnetic locking. When two unlike poles are brought near each other, its magnet is strong. There exists a thermodynamic force of attraction between two poles. In such condition, the two magnets are said to be magnetically locked. If now one of the two magnet is rotated and other is also rotating in the same direction with, with the same speed due to the force of attraction, that is due to the magnetic locking condition. So to have a magnetic locking condition, there must be exist two unlike poles and magnetic axis of two must be brought each very close to each other. Let us see the application of this principle in case of synchronous motor. Consider a, a three-phase synchronous motor whose stator is wound for two poles. The two magnetic fields are produced in the synchronous motor by exciting both the windings, stator and rotor, with three-phase AC supply and DC supply respectively. When three-phase winding is excited by the three-phase AC supply, then the flux is produced by the three-phase winding is always rotating type, which is which is already produced by the three-phase winding is always rotating type. As the magnetic flux rotate in space, at a speed is called synchronous speed. This magnetic field is called rotating magnetic field. Rotating magnetic field create the effect similar to the physical rotation of magnet in space with the synchronous speed. So stator of the synchronous motor produce the one magnet which is synchronous speed, which is very good and as rotating in space with a synchronous speed. The synchronous speed of a stator rotating magnetic field depend on the supply frequency and the number of poles for which a stator winding is wound. If the frequency of the AC supply is F Hertz and the stator is wound for P number of poles, the speed of the rotating magnetic field is synchronous given by Ns is equal to 120 F by P RPM. In this case, a stator is wound for say 2 poles with 50 Hz supply. The speed of the rotating magnetic field will be 3000 rpm. This effect is similar to the physical rotation of two poles with a speed of ns rpm. For simplicity, for understanding, let us assume the stator poles are n1 and s1, which are rotating at same speed ns. The direction of the rotation of rotating magnetic field is say clockwise. When field winding is on the rotor is excited by the DC supply, it also produces the two poles. Assume a rotor construction to be two poles alien type. Let these poles be N2 and S2. Now one magnet is rotating at Ns having poles N1 and S1, while its start rotor is stationary. That is second magnet is stationary having poles N2 and S2. If somehow the unlike poles N1 and S2 or S1 and S2 are brought near each other, the magnetic locking may be established between stator and rotor poles. As rotor poles are rotating due to the magnetic locking, rotor will rotate in same direction. As that of stator poles is the direction of rotating magnetic field, the same speed, that is ns. Hence, the synchronous motor rotate at one and only one speed, that is synchronous speed. But this all depend upon the existence of the magnetic locking between stator and rotor poles. Practically, it is not possible for stator poles to pull the rotor poles from stationary position into magnetic locking conditions. Hence, the synchronous motor is not self-starting motor. Um, Actually, why synchronous motor is self-starting means let us consider on rotating magnetic field as equal to physical rotation of the two stator poles N1 and S1. Consider at the instant when two poles are at such position where stator magnetic axis vertical along AB. Consider this diagram. At this instant, rotor poles are arbitrarily positioned. At this instant, rotor is stationary and unlike poles will try to attract each other. Due to this, rotor will be subjected to a instantaneous torque in anti-clockwise direction. Now, stator poles are rotating very fast, that is at a speed of ns rpm. Due to inertia, this would rotor hardly rotate in the direction of anti-clockwise torque to which is subjected. The stator poles change their positions. Consider an instant half of period later where the stator poles are exactly reversed, but due to the inertia, rotor is unstable to rotate from its initial position. At this instant, due to the unlike poles trying to each other, the rotor will be subjected to a torque in clockwise direction. This will tend to rotor to rotate in the direction of the rotating magnetic field. But before this, it happens that stator poles again change their positions, reversing the direction of the torque exerted by the rotor. As a result, the average torque exerted on the rotor is zero, and hence the synchronous motor is not self-starting. Next one is the methods for starting the synchronous motor. Actually, the synchronous motor is not self-starting, so some methods will be used to starting the motor. There are four methods we are having. First one is using pony motor, that means small induction motor. Next one is using damper winding. Next one is using DC motor. Next one is starting as an induction motor. First of all, we have to see about using pony motor. In this method, the rotor is brought to the synchronous speed with the help of some external device like small induction motor. Such an external device is called pony motor. Once the rotor is attained the synchronous speed, the extension of the rotor is switched on. Once the synchronism is established, pony motor is decoupled. The motor then continues to rotate as a synchronous motor. Next one is by using the damper winding. In a synchronous motor, in addition to the normal field winding, the additional winding consisting of copper bars placed in the slots in the port spaces. The bars are short circuited with the help of N rings. As an additional winding on the rotor is called damper winding. This winding is short circuited as a squirrel cage rotor winding of the induction motor. Once the stator is excited by three-phase supply, the motor starts rotating as an induction motor at subsynchronous speed. Then DC supply is given to the field winding. At the particular instant, the motor gets pulled into synchronism and starts rotating at a synchronous speed. As rotor rotates at synchronous speed, the relative motion between damper winding and the rotating magnetic field is zero. Hence, the motor is running at synchronous speed. There cannot be induced EMF in the damper winding. So, damper winding is active only at start to run the motor in the induction motor at start. Afterwards, it is out of the circuit. As in damper winding short circuit, the motor gets started as an induction motor. It draws high current at start. So induction motor started like start delta auto transformers etc. used to start the synchronous motor as induction motor. Next one is by using the damper winding. Many times this large synchronous motors are provided with a coupled DC machine. This machine is used as a DC motor to rotate the synchronous motor at a synchronous speed. Then the excitation to the rotor is provided. Once motor starts running as a synchronous motor, the same DC machine acts as the synchronous DC generator called exciter. The field of the synchronous motor is then excited by the exciter itself. Next one is the synchronous motor as a slip-in induction motor. The above method of the starting a synchronous motor as a squirrel cage induction motor does not provide the high starting torque. So to achieve this, instead of shorting the damper winding, it is designed to form the three-phase star or delta connected winding. The three end of this winding is brought out through a slip ring. The external rheostat then can be introduced in series with the rotor circuit. So when stator is excited, the motor starts as a slip ring induction motor, and due to the resistance added to the rotor provides high starting torque. The resistance is then gradually cut off. The motor gathers speed. When the motor attains is near synchronous, the DC excitation is provided to the rotor. The motor gets pulled into synchronism and starts rotating at synchronous speed. The damper winding is started by shorting the slip ring. The initial resistance added in the rotor not only provide the high starting torque but also limit the high interest current of the starting current. Since it acts as the rotor resistance method, actually here the same three-phase rotor winding act as the normal rotor winding by shorting two of the phases. From the positive terminal, current I flows in one of the phases, which is divided into two phases at start point as I by 2 each through each when switch is turned to the DC supply side. Uh, Next one is power angle of synchronous motor. The synchronous motor rotating at synchronous speed, but increase in the shaft load causes the rotor magnet to change in angular position with respect to the rotating flux of the stator by electrical angle del. This angle is called the power angle or load angle of the induction, synchronous motor. Next one is V curve and the inverted V curve. Actually, the excitation can be increased by increasing the field current passing through the field winding of synchronous motor. If graph of the armature current drawn by the armature motor current against the field current is plotted, then its shape looks like the English alphabet V. If such graphs are obtained at various load conditions, we get the family of curves looking like V. Such curves are called V curve of the synchronous motor. As against this, if the power factor cos phi is plotted against the field current IF, then the shape of the graph looks like inverted V. Such curves obtained by plotting power factor against IF at various load conditions are called inverted V curves of synchronous motor. Uh, Next one is handing in the synchronous motor. Actually, it is seen that when synchronous motor is on no load, the stator and rotor poles axis almost coincide with each other. When motor is loaded, the rotor pole's axis falls back with respect to its stator. The angle by which rotor retrads is called the rotor angle or angle of retraction del. If the load connected to the motor is suddenly changed by the large amount, then rotor tries to retract to take its equilibrium position. But due to inertia of the rotor, it cannot achieve its final position instantaneously. While achieving its equilibrium position due to inertia, it passes beyond its final position corresponding to new load. This will produce more torque than what is demanded. This will try to reduce the load angle and rotor swings in other direction. So there is periodic swinging of the rotor on both sides of the new equilibrium position corresponding to the load. Such oscillations of the rotor about its equilibrium position due to sudden application of or removal of the load is called swinging or handing in synchronous motor. Due to synchronous handing, the load angle changes. That means load angle del changes its value about its final value as del changes for some excitation, that is ED phase. The current drawn by the motor also changes. Hence during handing there are changes in the current drawn by the motor which may cause problem to the other applications connected to the same line. The changes in the armature current due to handing is shown in one figure. the oscillations continued for longer period, there are large fluctuations in the current. If such variations synchronized within a natural point of oscillations of the rotor, the amplitude of the swing may become so great that motor may come out of the synchronism. At this instant, mechanical stress on the rotor are severe and current drawn by the motor is also very large. So motor is subjected to the mechanical and electrical stresses. The causes of the hunting of synchronous motors are sudden change in the load, sudden change in the field current, the load containing harmonic torque, fault in supply system. The effect of the hunting in synchronous motor is it may lead to loss of synchronism, it produce the mechanical stresses, increase the machine loss and cause temperature rise, cause great surges in current and power flow. The reduction of synchronous hunting in synchronous motor is by using the damper winding. Um, Actually, it is mentioned earlier that is in lots of alternating pole phases, a short circuited winding is placed. This is called damper winding. When rotor starts oscillating, that is when hunting starts a relative motion between damper winding and the rotating magnetic field is created. Due to this relative motion, EMF gets induced in the damper winding. According to Lenz's law, the direction of the induced EMF is always as to oppose the cause producing it. This cause is the hunting. So such induced EMF opposes the hunting. The induced EMF tries to damp the oscillations as quickly as possible. Thus hunting is minimized due to the damper winding. The time required by the rotor to take its equilibrium position after hunting is called setting time on the rotor. If the load angle till is plotted against the time, the magnetic representation is called hunting. Uh, Actually, it is reduce the setting time of the rotor. Next, by using the flywheels, by providing a large and heavy flywheel to the prime mover, its inertia can be increased within the turns, help of the maintaining the rotor speed constant. Next one is synchronization with the infinity bus bar. There is a specific procedure for connecting a synchronous machine to infinity bus bar. The concept of infinity bus bar is already explained in the previous chapter. Similarly, the process of synchronization is discussed in detail by using various methods with the help of the special device called synchronous scope. Infinity bus bar is one which keeps the constant voltage and frequency through the load varies. Actually, the synchronous machine which is to be connected to the bus bar with the help of switch K. If the synchronous machine is running as a generator in a phase sequence should be same as that of bus bar. The machine speed is and field current is adjusted in such a way to have the machine voltage same as that of bus bar voltage. The machine frequency should be nearly equal to bus bar frequency so that the machine speed is nearer to synchronous speed. When the above conditions are satisfied, the instant of switching for synchronization should be determined. This can be determined by lamp dark methods, lamp bright method, lamp bright and dark method by using the synchronous loop. Once switch K is closed, the stator and the rotor field in the machine lock into the each other and machines then runs at synchronous speed. The real power exchange with the main will be now governed by the loading conditions on the shaft, while the reactor power exchange will be determined by the field excitation. The same procedure is to be followed by the synchronization of the synchronous motor to the infinity bus bar. The motor is run by the auxiliary device as a small DC or induction motor initially and then the synchronized to the bus bar. As we know that the synchronous motor are not self-starting, hence if switch K is closed when rotor is stationary, the average torque will be zero as the two fields run at synchronous speed relative to each other. So the motor fails to start, they made they are made self-starting by providing a short-circuited bars on the rotor which produce torque as they produce in case of induction motor. Next one is the synchronous condenser. When synchronous motor is overexcited, it takes leading power factor current. If synchronous motor is a no load, where load angle del will be very small and it is overexcited, then power factor angle increase almost up to 90 degree and the motor runs with almost zero leading power factor condition. This characteristic is similar to the normal capacitor which always takes leading power factor current. Hence overexcited synchronous motor operating on the no load condition is called synchronous condenser or synchronous capacitor. This is a property due to which synchronous motor is used as a phase advancer or as power improvement device. Next one is the use of synchronous condenser in power improvement method. Uh, the low power factor increase of the cost of generation, distribution and transmission of the electrical energy. Hence, such a lower power factor needs to be corrected. Such power factor correction is possible by connecting synchronous motor across the supply and operating it on the no load with overexcitation. Now that V phase is the voltage applied and I1 versus the current lagging V phase by angle pi 1. This power factor pi 1 is very low lagging. The synchronous motor acting as a synchronous condenser now is now connected across the same supply. This draw the leading current of I2 phase. The total current drawn from the supply is now phasor of I phase and I2 phase. This total current IT now lag V phase by smaller angle pi, due to which effective power factor gets improved. This is how the synchronous motor as a synchronous condenser is used to improve the power factor of the combined load. As the power factor became very decreased, that means very low, the current drawn from the supply increased to the supply same power to the load. But if power factor maintained high, the current drawn from the supply is less. The high current due to the low power factor has following disadvantages. The higher current conductor size required is more, which increase the cost. The power factor is given by cross price equal to active power by apparent power. Thus, for fixed active power P, the lower power factor demands large kilowatt amp rating alternators and transformers. This increase the cost. The large current means the copper losses and poor efficiency. Large current causes large voltage drop in transmission line, alternators and other equipments. They result in the poor regulation. To compensate such drops, extra equipment is necessary in which further increase the cost. Next one is torque in the synchronous motor. There is four torque will be presented in the synchronous motor. One is starting torque, other one is running torque, and the pulling torque, pull out torque. First one is starting torque. This is a torque developed by the synchronous motor at a start when the rated voltage is applied to the stator. It is called the backplate torque. It is necessary to overcome the friction and inertia. Next one is running torque. It is a torque developed by the motor under running condition. It is determined by the output rating of the motor and speed of the driven machine. Next one is pulling torque. Initially, synchronous motor is rotated at a speed slightly less than the synchronous speed. When speed is near to synchronous, excitation is switched on and the motor gets pulled into synchronism and starts rotating at the synchronous speed. The amount of torque developed by the motor at the time of pulling into synchronism is called pulling torque. Pull out torque. When the synchronous motor is loaded, the rotor falls back with respect to stator by an angle called load angle del. As del increased, magnetic locking between stator and rotor decreased. At del equal to zero, the torque developed by the is maximum by the motor. and the mantle again is very weak. Any further increase in the load pulls motor of the synchronism and motor stops. Thus, the maximum torque developed by the synchronous motor without pulling the synchronism is called the full out torque. Next one is features of the uh, synchronous motor. The synchronous motor only runs at synchronous speed. By varying its excitation, the power factor can be varied. Axis can be operated in leading power factor. It is used as a power factor correction device. Next, this motor is the not self-starting and requires the additional facility to make it self-starting. Next one is uh, under no load and over-excited condition, it can be used with synchronous condenser. Next one is the application of synchronous motor. The important characteristics of the synchronous motor is the constant speed irrespective of the load condition and variable power factor operation. As seen earlier, its power factor can be controlled by controlling its excitation. For over-excitation, its power factor is leading in nature, which is very important from the power factor correction point of view due to constant speed characteristics. It is used in the machine tool, motor generator, uh, generator set, synchronous clock, next timing device, robot devices, belt drive and reciprocating pumps, and fans, blowers, centrifugal pumps, vacuum pumps, plug grinders, textile mills, paper mills, line shaft, rolling mills, cement mills, etc. The synchronous motors are often used as the power factor correction device. Uh, Phase advanced and phase modifiers for voltage regulation of the transmission line. This is possible because excitation of synchronous motor can be adjusted at the requirement. Then the disadvantage of the motor is it is heavier cost, the necessity of the frequent maintenance, not self-starting, hence additional starter device will be required. Separate DC source required for exciting the rotor, sensitivity to sudden load changes causing hunting, requires lifting and brushes. Mm, the advantage of the synchronous motor is by changing the excitation, power factor will be varied. It can be used as synchronous condenser for improving power factor. It can be used always the speed is constant, so irrespective of load. Electromagnetic power varies linearly with the voltage. Next one is if we started the motor at faulty starting, uh, which can be occur means the rotor is not driven up to record speed by external device. The DC supply to the rotor is not given. Next one is if the motor is a lower power factor means some disadvantage will be occur. They are for low power factor current drawn is high. Next one is for the higher current conductor sizes required is more which increase the cost. For fixed active power uh, for fixed active power P, the low power demands large kVA rating, alternators and transformers. This increase the cost. Large current means more copper loss and poor efficiency. The large current causes large voltage drops in transmission line. Alternators and other equipment result in the poor regulation. Next, there are many type of excitations will be in the synchronous motor. That is normal excitation, under excitation, and over excitation, critical excitation. First one is normal excitation. When this excitation is adjusted to get EB equal to V, that is induced EMF is equal to the applied voltage. Such an excitation is called normal excitation of the motor. Next one is when the excitation is adjusted in such a way that the magnitude of the induced EMF is less than the applied voltage, that means EB less than V. The excitation is called under excitation. Next one is the excitation of the field winding for which the induced EMF become greater than the applied voltage. That means EB greater than V. Then it is called overexcitation. When the excitation is changed, the power factor changes. The excitation for which power factor's motor is unity, that means cos phi is equal to 1. It is called uh, critical excitation. Now another one important topic is a synchronous motor on no load and synchronous motors on load. Okay, first one is the synchronous motor on no load. If the synchronous motor will be not connected to the load, the magnetic locking exists between the stator and rotor, but in such a way that there exists a small angular difference between the axis of two magnetic field. So the rotor falls back with respect to stator axis by angle del. This angle decides the amount of current required to produce the torque to various supply various losses. Hence, this angle is called load angle, power angle, coupling angle, torque angle, or angle of retardation. Denoted as del as mentioned earlier. Next one is the synchronous motors on load. As a load on the synchronous motor increase, there is no change in its speed, but what gets affected is the load angle del, that is angle by which rotor axis retracts with respect to stator axis. Hence load increase, del increase, but speed remains synchronous. As del increase through EB phase and B phase, magnitude are same. Displacement of EB phase from its ideal position increase. Hence the vector difference between E phase minus E phase increased. As synchronism impedance is constant, the magnitude of I phase torn by the motor increased as load increase. This current produces the necessary torque which is satisfy the increased load demand. The magnetic locking still exists between the rotor and stator. Next one is constant excitation angle. Actually, when del increased, the magnetic flux in producing the force of the attraction between the two get will be more unstretched. This weakens the force maintaining the magnetic locking. Through torque produced by the motor increased. As del reaches up to 90-degree electrical, that is half of the pole pitch, the stretch flux lines gets broken and hence magnetic locking between the stator and rotor no more excited. The motor comes out of synchronism. So torque produced at del equal to the 90-degree electrical is the maximum torque a synchronous motor can produce. Maintaining magnetic locking, that is synchronization. So this torque is called pull out torque. Okay. Next one is synchronous motor is connected to the infinity bus bar. The synchronous motor is connected to the infinity bus bar. Behaves similarly for the change in the load at constant excitation. As the load increase, the load angle increase, current increase, and power factor changes. The changes in the power factor depend upon the excitations used in the synchronous motor, whether it is normally excited or overexcited or it is underexcited. Thus, effect of change in the load on synchronous motor connected to the infinity bus bar is summarized as the irrespective of excitation, the load increased, the load angle del and armature current IA will be increased. When the motor is normally excited, then the load increase, the change in the current is more significant than the change in the power factor. The power factor tends to become more and more lagging as the load increases. When the motor is overexcited or underexcited, the power factor changes are more significant than the changes in the current in load angle. Load changes. When the motor is overexcited or underexcited, the power factor tends to be approached to unity as the load increases. Next one is uh, the variable operations of the synchronous motor. That means variable excitations. We already see that. Now we have to see the power flow in the synchronous motor. Actually, the net input power is equal to Pn. Pn is equal to root 3 VLIL cos phi. That means power equation is equal to voltage into current and the phasor angle between voltage and current. Okay. So VL is equal to applied line voltage, IL is equal to applied line current, cos phi is equal to power factor. Then Pin is equal to 3 V phase I phase cos phi. Next, the stator loss is equal to 3 into I phase square into RA. Now we have to write the power developed is PM. So PM is equal to Pin minus stator copper loss. That P is equal to T into omega. That omega is equal to 2 pi ns divided by 60. So Tg is equal to Pm into 60 divided by 2 pi ns. For lagging power factor, pi minus del. For leading power factor, pi plus del. For unity power factor, del. Then while calculating the angle between E phase and I phase, that means phase and current, bit current and angle between phase and current and voltage from phasor diagram, it is necessary to reverse the EB phase phasor. After reversing EB phase, I phase, as it is opposition to the V phase, the angle between E phase and I phase must be determined. In general, PM, that means power developed, that means gross power is equal to 3 EB phase IB phase cos plus or minus del. Okay, for it is lagging or leading. Positive sign for the leading power factor and the negative sign for the lagging power factor. Net output of the motor then can be obtained by subtracting friction and windage, that is mechanical loss from the gross and mechanical power developed. P out is equal to PM minus mechanical losses. And T shaft. T shaft means torque developed in the shaft. Okay, that means in motor shaft is equal to P out divided by 60 divided by P out into 60 divided by 2 pi ns Newton meter. Then T shaft means shaft torque of the load. P out means power available of the load. Percentage efficiency is equal to normally efficiency is equal to output divided by input. So power means power output divided by power input into 100 percentage. Next one is condition for the maximum torque. The condition for the maximum torque is equal to when RA is negligible, that means resistance, armature resistance is negligible, theta is equal to 90 degree, the maximum torque will be developed. This torque is called the pull out torque. Okay, uh, this torque is called the pull out torque. Next one is the two reaction theory of the synchronous motor. The two reaction theory, when two reactors according to this theory are direct action reactants X3 and contract action reactants X2, the motor offers current of two components ID and IQ. The phasor diagrams for the lagging power factor will be considered. Actually, in two reaction theory, we have to find the leading power factor of the synchronous motor. Next one is the Blondel diagram. The Blondel diagram is the diagram for synchronous motor, is an extension of the simple phasor diagram of the synchronous motor. Let us consider the power equation. Pn is equal to V phase I phase cos phi is considered for the Blondel diagram. Actually, here we have to find the constant power cycle of the synchronous motor. Next one is equal to disadvantage of the lower power factor. Actually, in disadvantage power factor means actually most of the machines are induction type motor. The lighting of the heating load of these supplied through the transformers. The induction motor and transformers are lagging current from the supply. Since overall power factor is low and lagging in nature, so for the low power factor, all power factor will be low. Okay. It may cause the conductor size is increased and the efficiency will be low and the loss will be increased. Next one is equal to synchronous capacitor. Synchronous capacitor means when the synchronous motor is on no load, it will be more excited than the power factor of the synchronous motor increased almost 90 degree and the motor runs almost zero leading power factor condition. This is exactly identical to the bigger the synchronous capacitor. This is called synchronous capacitor. Uh, Next one is the applications of the synchronous motor. It will be used in the power factor improvement and the speed is applications may be find the application when the operating speed is less and high power required. Then it will be used in the power factor improvement condition. That means synchronous capacitor. Next will be used in the pump, compressor, clippers and mixer. Thank you.